Okay, so here I'll be going over the 4 FRQs from the progress check and going over any additional details that aren't necessarily provided by the solution. So you should be able to see the solutions when you submit the FRQ, and it allows for self-scoring. It's going to give you the scoring guide. But here I'm going to kind of walk you through the problems and kind of show you how to think about them. So here we have a classic. This is actually very similar to the one that was on the problem set. We're looking at this block that is moving along the track, and then it's going to go through this loop-de-loop, and then it's going to get launched at position C. So it's going to be compressed by the spring, gives it some kinetic energy at point A, then it's at point B going through the loop-de-loop, and then at point C it's just going to launch straight up in the air. So for part A, it says when the block reaches position B, the normal force is exerted on the block by the track is equal in magnitude to the gravitational force. So that is a critical piece of information that you need in order to solve for part 1 of part A. So we have to derive an expression for the speed of the block at position B, okay? Just using m, k, r, and physical constants as appropriate. So at position B, okay, what you need to understand is that there has to be a centripetal force acting on the block, okay, because it's going around in a circle. And since the normal force exerted on the block by the track is equal to the force of gravity, we can draw that as a free body diagram. So it's telling me that there's a normal force being exerted on the block. Okay, actually here I'll use black here. And there's a force of gravity, and these two forces are equal. All right, so we know that the weight of an object is equal to mg, and then we're setting it equal to the normal force, right? And these two forces combined are going to provide the centripetal force, right? So the centripetal force acting on an object is equal to mv squared over r. And basically, it's the net force that's acting on the object, right? That describes how the object is accelerating, right? In order to have a centripetal force, there has to be a centripetal acceleration that's equal to the net force on the object. So here we have normal force pointing towards the center of the circle, and we have the force of gravity pointing towards the center of the circle. So both of these forces are contributing to the centripetal force that's acting on the block. All right, so I'm going to set this equal to Fn plus mg, and we know that the normal force has to equal mg because it says so in the problem. So it's just 2 times mg. All right, so I have mv squared over r equals 2mg. All right, so I'm just going to write that out. mv squared over r equals 2mg. Well, the m's cancel out, right? And then we're just solving for r. So we have v squared is equal to 2 times g times r. And then I just take the square root. So square root of 2gr. Here, I'll put capital R because they use capital R. All right, so that's the first part. Second part, block leaves the track at position C and continues traveling vertically before reaching its maximum height. Derive an expression for the distance that the spring was compressed before the block was released. So for this one, I think it's helpful to kind of keep track of the energy in the system. So we start off with just potential energy in the spring, 1/2 kx squared. Then it's going to have some kinetic energy here, 1/2 m times v sub a squared. And then here it actually has potential energy and kinetic energy, right? So it has 1/2 m v sub b squared plus mgh, which in this case h is 2r, right? Because if I have I'm at the top of the circle, right? So the diameter of the circle is just 2 times the radius. That's how high it is off the ground. Okay, so I'm just going to put plus 2r. And then here at point C, when it reaches its max height, we know that it... so we're not sure exactly how high it reaches based on the radii. We can figure that out later. But I know that its final potential energy is going to be mghf. Okay, so let's actually get around to figuring that out. So one thing that you can do is we're going to use our expression from before. So we know what the velocity at point B is. It's the square root of 2gr, all right? And we know that the energy is stored initially in the spring, 1/2 kx squared. Then we have this energy over here, the kinetic energy plus potential energy, and we know that has to equal the final potential energy. So I'm going to write that all out. 1 half kx squared. So what are we trying to find? So we're trying to find the distance that the spring was compressed before the block was released. Okay. All right. So 1 half kx squared equals 1 half mVA squared. We don't know what VA is, but we do know what VB is, right? So this is the energy when it's compressed. Here's the energy at point A. It's all kinetic energy. At point B, it's a mix of kinetic energy and gravitational potential energy. So we have mg times 2r. And we're not going to worry about point C. We don't have to worry about it for this part of the problem. So we're trying to solve for x, all right? So I'm going to just ignore the energy at point A because we don't have any information for that. But I do have information about the energy at point B. So now I'm going to substitute in the expression for the velocity at point B. So I have 1 half times m times 2gr, right? So remember that the velocity at point B is square root of 2gr, but I have VB squared over here. So I'm just going to put 2gr over here. Plus mg times 2r. All right, and let's start combining some terms. So here I have 1 half m times 2gr. Well, the 1 half and the 2 kind of cancel out. So we have mgr plus 2mgr, and that's just 3mgr, right? So I have 1 half kx squared equals 3mgr. Okay, I'll just be very thorough just so we don't get lost. Mgr, multiply both sides by 2, kx squared equals 6mgr. All right, and then I'm going to divide both sides by k and then take the square root. So I have x is equal to the square root of 6mgr over k. And that's it for that one. That's part 2. Here's part 1, and there's part 2. Part 3, indicate how the maximum height of the block reaches compares to the height at position B. Justify your answer without manipulating equations. Okay, so what I'm going to do is, I'm going to solve it anyways, right? For the sake of time, I think it's helpful to see how to solve it, but obviously on the actual test, you're just going to want to move quickly, right? So if you don't need to manipulate equations, don't manipulate equations. But let's think about it. So when I reach maximum height, right, my velocity is 0. This is getting projected straight up, right? So this block is getting projected straight up, and it's going to reach some maximum height where the vertical velocity is 0. It's not going to have any horizontal velocity. Basically, it's 0 velocity. So I know that the way I would explain this is that at point C, or actually, it's not even asking about point C. It's asking about the maximum height. So point C is when it actually gets launched off. All right, so at maximum height, so at max height, right, all of the mechanical energy is stored as gravitational potential energy. Yeah, I'll just write it out. Gravitational potential energy. Whereas at position B, it is split between, I'm just going to put GPE and KE for the sake of time. Write it all out. It's split as gravitational potential energy and kinetic energy. And we know that the energy, there's no mechanical energy that's lost. So if more of the energy is stored as potential energy, that's why it reaches a higher height. Okay, that's the basic idea. If you want to calculate it as an extra, okay, what you could do is, so I think I wrote MGHF, right, for the final energy somewhere. Yeah, right here. So MGHF, this is just extra. This is just for your understanding. You don't have to do this because that's not what the question's asking for, but I just want to show you anyway. So this is where we have this term here, right? So we know that the 3 mgr, right, that represents the energy of the system when it's at the top of the loop-de-loop, right? So I know that this is equal to 3 mgr. So the mg's cancel out, and I know that the final height is 3r. All right, so at position B, it's at a height of 2r, and then the rest of the energy is stored as kinetic energy, and then at max height, it's all potential energy. And I can even graph it just to really make sure we understand the energy flow. So this is going to be at position B. I'm going to look at the total mechanical energy, and I know that it's split up as kinetic energy and potential energy. So the potential energy is going to be 2 mgr, and then the kinetic energy is just mgr. And then at max height, all of the energy is going to be potential. All right, this is just extra. You don't have to do this. I'm only doing this to make sure we understand what's going on in the problem. We understand how the energy is flowing in the system. Okay, so next problem. All right, so we're moved to a different track. There's no circular loop, okay? And we need to figure out that, let's see, it goes through some kinetic friction over a distance of 3r. There's mu sub k, and then it reaches a max height of 2r. We have to derive an expression for the speed v naught that the block must have at position A in order to reach a maximum vertical height of 2r. All right, so here I know I have some initial kinetic energy, 1/2 m v naught squared. That's at position A. Then here, where there's friction, I'm actually going to lose energy. All right, so friction does negative work, right? So there's negative work from friction, right? And the idea as to why there's negative work, I know that as the block is moving through this region, right, friction is going to exert a force that opposes the motion of the block while the block is displacing in this direction. All right, so these vectors in opposite directions, right, if we just do fx cosine theta, right, they're in opposite directions, cosine 180, that equals -1. All right, so when they're, friction is just going to do negative work, right? That's just, what's going on in this case. So I'm going to have some energy loss due to friction, and then it's going to reach this max height of 2r. So this energy is stored as potential energy. So mg times 2r. That's the height that it reaches. All right, and then obviously the velocity here is 0 at max height. So all the energy stored is mg times 2r. So here I have mg, 1/2 m v naught squared, and I'm going to subtract the work done by friction, and that should equal how much energy I have left at the end. All right. In terms of the work done by friction, well, now we have to write it out in terms of the constants. So as a refresher, free body diagrams, we know there's a force of friction acting on the object. There has to be a normal force that's holding it up. And obviously, this is the force of gravity equal to mg. And we know that the equation for friction, for kinetic friction, mu sub k times normal force has to equal mg. So mu sub k times mg, right? Now for work is force times distance, right? So here it travels a distance of 3r. So the work done by friction, I'm just going to write negative, let's see here. All right, so I know that my force is mu sub k times mg, and the distance is 3r. All right, so that times 3r. I know I wrote it as a negative here, but I'm already kind of encoding that with this equation here. Right, I understand that with this equation, the mu sub k times mg times 3r, that's like the magnitude of the work that's being done by friction. And I already understand that it's that energy is going away, right? So my initial kinetic energy minus the work done by friction, that equals my final potential energy. So if I combine all this together, I have 1/2, so 1/2 m v naught squared minus 3 times mu sub k times mgr. That has to equal my final potential energy, which is mg times 2r. I'm just going to write that as 2 mgr. 2 mgr. Okay, so let's get rid of the m's. So we know the m's cancel out because there's an m in every single term. And we're trying to solve for mu sub k. So I'm just going to rewrite this expression. So I have 1/2 v naught squared. I'm going to move this 3 mu sub k times r to the other side, and then move this 2 gr over to this side. If I go through every algebra step, it'll take too long. All right, so work out these problems along with me, and you'll see how the algebra is working out. All right, so here's my expression here. I got to solve for mu sub k. So I'm going to divide both sides by 3gr. Right, so actually, let's see how I want to simplify the expression. Because that looks a little, I want to keep all the terms kind of together. I mean, it should be fine. You could do it like this. So you have mu sub k is equal to 1/2 v naught squared minus 2gr, all divided by 3gr. But that's looks a little unpleasant. To be a little bit more clean with the algebra, I'm just going to combine the grs together, right? So I don't have grs in multiple terms. So writing this out, let me use a different color. So write it out in blue, because that's also how it shows in the solution manual. So they have 1/2 v naught squared is equal to 2gr plus 3 times mu sub k times gr. All right, and then they multiply everything by 2, and then they factor out a 2gr. So v naught squared is equal to 2gr times 2 plus 3 mu sub k. All right, and then, oh wait, actually we're not deriving mu. Whoops. We're deriving v naught. And that's where I got to be careful. All right, so here, yeah, you just get v naught is equal to the square root of 2gr times 2 plus 3 mu sub k. All right, yeah, it's the same algebra steps here. I thought I was solving for mu sub k. Yeah, you just add the 2gr over here, and then you times everything by 2. It's the same idea. 3 mu sub k times gr plus 2gr, right? And then you can factor out. You get the same result. All right, so that's the answer. So the initial velocity of the block is the square root of 2 times g times r, all multiplied by 2 plus 3 times mu sub k. And then all that's under a square root. All right, just to make it a little bit more legible. So that's the final answer. Alrighty, so that was it for that FRQ. All right, let's move on to the next one. Let's see, let's go to, where's FRQ number 2? Here we go. All right, so I'll mark up this one. All right, so let's see here. Here we have a cart that's going down an inclined plane. It's tied by a piece of string, and it is at rest, right? It's held in place. So we know the forces have to balance. We have to draw and label the forces. And yeah, let's look at our free body diagram. All right, so we have a normal force that's going up and to the right. Okay, so they already kind of rotated the free body diagram so that this is going, oh no, what happened? All right, so this is going down the plane. All right, so it's going down the plane. So we got to label all of our forces. We know that gravity is going to go straight down. All right, so this is our force of gravity. You can put force of gravity. They're also okay with writing mg, but I like using this notation, capital F. And then here we know that there's some tension in the string. Okay, I'm going to put force tension. Now the relative size of the arrows are important. So something this is actually fairly important. So notice that when I drew the force of gravity, the vertical component of the force of gravity is about 4 units large, right? And you see how the normal force is about 4 units in magnitude, right? So those the mg cosine theta, you're not going to draw the component on the free body diagram. So don't draw the components, but you just need to make sure that the component that's perpendicular to the plane, is has this same magnitude and is in opposite direction of the normal force. And the same is true for the force of tension, right? So if I labeled. All right, actually, so I drew out the force of gravity here. So the force of gravity is going straight down, and it's about 3 units across, parallel to the plane. All right, so this thing's in equilibrium. So that tension force also has to have a magnitude of 3 units going up the inclined plane. So yeah, the relative sizes of force vectors, especially when they give you a grid, that's how you know you got to be careful about the size of your force vectors. So I'm pretty sure in the scoring guidelines they go over that. Actually, did I draw this crooked? I guess I did draw it a little crooked. Well, I mean, actually, did it even score points for this? Let's see here. Forces have a vector sum of 0. Okay, so yeah, that's the point. So the fact that if they have a grid, so I drew it a little crooked, but it's practically going straight down. I mean, it looks straight down to me. The example response they gave was slightly less. All right, but whatever the components are, right, they have to actually match. So the way I drew the force of gravity, it has a component that's parallel to the plane. It's about 3 units. So I drew the same length for the tension force in this case. Okay, so anyways, let's see here. All right, we did the free body diagram. And honestly, the free body diagram is worth quite a bit of points, right? So what was that worth? 3 points or 2 points? 3 points, all right? So making sure you correctly labeled your forces, okay? So correctly labeling the tension force is going up and to the left, and that's equal to the component of the gravitational force, and then that they have a vector sum of 0. All right, so the free body diagrams, don't blunder points on these, all right? Actually take your time, draw it right, double check, and then move on, because they're worth quite a bit. All right, now this part of the problem. This is going to be a fun one. So I'm just going to go over the solution that they provide, and I'm going to kind of explain it using many different kind of representations of what's going on. But let's kind of break down the problem because this is one that's definitely a little tricky to fully understand. And if you just look at the solution, it doesn't give you a clear picture as to what's really going on. All right, so let's kind of evaluate what's happening. So this cart is going to slide down, and it's going to experience there's going to be a conservative force that's acting on the cart. All right, so when it says there's a conservative force, that means that it obeys the law of conservation of mechanical energy, and you can represent a potential energy function for that given conservative force, right? So you can think of it, it's kind of like a spring. It's not a spring, but it's in the same, it's the same idea, right? You have some force that is gonna be path independent, right? So we have this conservative force, and what's annoying is it's a piecewise conservative force. So the conservative force changes as it goes along the track. I'm not sure how exactly they would set that up. A physical interpretation could be, I was trying to think of a good way to explain it. It's a car with, perfect regenerative braking that is wonky, right? Or there's some weird thing with electric fields. There's not really a physical analog. It's more just testing your ideas. Do you understand how conservative forces are connected to the potential energy, right? That's what this is really testing for. So here, something to clarify, I have a force function that from the region of 0 to x naught, it is equal to negative bx. All right, so in this region, it's a variable force, right? So the force starts off at 0 when x equals 0, and that force increases from x equals 0 to x naught. So it's kind of like acting like a spring, right? A spring has the same kind of equation, negative kx. So there's a variable force during the first region. Then during the second region, it's a constant force, right? So kind of like how gravity works, right? You have a constant conservative force. This one is negative b x naught. Actually, no, it's not like gravity. That's why this is a wonky kind of problem, because gravity varies. Well, No, it is kind of like gravity. Yeah, no, never mind. I take it back. This is obviously, a wonky kind of situation, but it's just testing to see if you understand how the conservative force connects with the potential energy. And then the force is zero at the very end. All right. So it's like it starts off like a spring, and then it's like gravity, and then there's no conservative force. All right, so what's important is being able to perform the integral. So here we have each region, we have an equation for f of x, we have to derive an equation for a potential energy function that results from f of x, and then we take u sub x to be 0 at x equals 0, and we're going to express u sub x in terms of bx, x naught, and physical constants as appropriate. Alrighty, so I think what's helpful in sort of understanding what's going on in the problem is to actually graph it, right? So say we have our force function here, and I know that I have these regions, x naught, 2x naught, 3x naught, right? So I'll label it here. I'm putting it up here because technically it's negative. So we'll see that from 0 to x naught, I have a force that is linear, okay? And it's going to reach some maximum value equal to negative bx naught, all right? So at x equals 0, the force is 0. At x equals x naught, the force is negative bx naught. Then from x naught to 2x naught, I have a constant force here, okay? And then suddenly, it drops all the way down to 0. All right. To get the potential energy function, right? So we know that the potential energy is equal to the negative derivative of the force. All right, so that's how you get the potential energy from a conservative force. All right. You don't have to plot it, but I'm going to plot it to kind of help you understand what's going on. But more importantly, we're going to actually just evaluate the integrals. All right. So here I already have them set up. And the way I do it is kind of different from how they do it. It has more to do with the concept of integration. I kind of want to do it that way because there are, that's the more mathematically pure way to do it. So let's just review what they write down. All right. So they evaluate the integral for every single region, but they take into consideration, right? So for the first region, I have this variable force that's equal to negative bx. And I'm going to evaluate it from 0 to x. And then my potential energy at x equals 0 is 0. So they're just calculating the change in potential energy, and they get 1/2 bx squared. The way I like to think about it, all right, it's the same, it's the mathematically equivalent, but it's just kind of incorporating what that constant of integration actually is, right? So let's write our function. So actually, another thing I'm going to do is, no, let's just evaluate the function first, and then I can kind of graph it to kind of help explain what's going on. So from x equals 0 to x naught, all right, we're going to evaluate our integral. So we have negative integral of negative bx dx. Now, I'm going to evaluate it from 0 to x, not 0 to x naught. You can do that, but it's not going to give you a function. It's going to give you a definite value, which is why I'm going to also graph it so I can kind of help explain it. And this is asking for a function. It's not asking what is the potential energy, the total potential energy in between these regions. All right, that's when you would go from the bottom of the region to the top of the region, and then you just kind of like add it all up. We're kind of writing a function. So we're going to have 3 different functions, right? Because I have 3 different functions for my conservative force. I'm going to have 3 different functions for my potential energy, and they're all going to be connected. So first, let's integrate this, all right? So I have the integral of negative bx dx, all right? So this is going to give me negative bx squared over 2, right? So as a reminder, with the power rule, if I'm integrating, say you're integrating x, so x dx. So the exponent is 1. So I'm going to add 1 to the exponent, and then I'm going to divide by by n plus 1. So I have, this is going to end up being 1 over n plus 1 times x to the n plus 1, right? That's the power rule for integration, right? So if I do that, I end up with negative 1/2 bx squared, but then there's a minus sign in front of here, so I have 1/2 bx squared evaluated from 0 to x, right? And I'm just going to x because I'm trying to write this as a function of x. All right, so here, something else that's important to note. All right, so this is where the initial potential energy comes from. So whenever you integrate something, right, this is something I want to clarify just because you may not have talked about this yet in calculus. But keep in mind that when you're integrating, that's the inverse function of the derivative, right? So when you're taking the integral, you're basically getting a function for the antiderivative. But you have to add something that's called a constant of integration. All right, and the reason the constant of integration exists is because if you take a derivative of a constant value, the derivative is 0, right? So you have to recover information about the function from the constant of integration. And this is just a side example, but it just kind of shows you how important this problem is in terms of like understanding how to actually do the derivatives and integrals and really know what you're talking about, right? So for example, right, let's do derivative of some function, right? Say we have x squared plus 1. All right, so I'm going to take a derivative of this function. And I'm going to end up with 2x, right? Because the derivative of x squared is 2x. Derivative of 1 is 0, right? So now I have this new function, f prime of x equals 2x. Now, if I integrate this function, I should get my original function back. But that's not the case if I don't consider the constant of integration, right? So now I'm going to integrate 2x, right? So let's integrate 2x dx. All right, if I integrate this function, I end up with x squared. So this is why we have to add that constant of integration, right? Because that information went away when we took the derivative. The integral of x of 2x dx, that's x squared plus c. And that c term, that's the constant of integration. And in terms of like, when are you going to use the constant of integration in physics, it has to do with these kind of problems where you have some initial condition. So you have some initial condition in the problem, and that initial condition gives you information about the constant of integration, right? So I'm connecting the pure calculus idea into something that's physically real. The initial condition in this problem is that mu sub x is 0 at x equals 0. The potential energy function is 0 at x equals 0. That's the initial condition. All right. I'm hoping that's making sense. If you're still confused about this topic, we can go over some more examples in class. But for the sake of time, I just kind of want to get into the problem. And I want to do it by using the constant of integration. So I have 1/2 bx squared plus c, and I'm going to evaluate this integral from 0 to x. And my initial condition is that at x equals 0, the potential energy is 0. And we're going to see how that plays a role here. So I'm going to evaluate from x equals 0, or from when, well, x equals x, and then from x equals 0. So I have 1/2 bx squared minus 1/2 b times 0 squared. And then let's not forget our plus c term. So this is just 0. So I just have 1/2 bx squared plus c, right? And my initial condition is that when x equals 0, the potential energy has to equal 0, right? So let's check it. If x is 0, this whole term is 0, right? So I'm going to set this equal to 0. That also means my c term has to be 0 in this particular problem. Now that's a bit anticlimactic, but you're going to see how it plays a role in the following expression. So I'm going to write the answer here. So my mu sub x is going to equal 1/2 bx squared from x equals 0 to x naught. All right, so now let's evaluate what the energy is like at x naught, right? Because now for my next problem, I have to look at from x naught to 2x naught. All right, so I'm going to write off to the side. My new initial condition is that my total potential energy at x naught is equal to 1/2 bx naught squared. All right, And this is where it comes from here. They're basically, that's what they're doing, is that constant integration is that they're looking at the change in the potential energy for each region, and they're including the potential energy from the previous region, right? So at the potential energy at x naught here, well, it's just 0, right? So that's where that constant integration comes in. And the same is true over here, right? So at x naught, we have 1/2 bx naught for the potential energy, and then we're going to evaluate this integral over here. Wait, where do I put my stuff? Over here. Okay. So now let's look at the next region. So now we're going to integrate. I'm going to start using different colors here. Well, it doesn't really all show up. So now we're going to do region 2. All right. So for region 2, now we're going to integrate the same function. Or actually, now it's a different function. So negative integral from x naught to x. All right. And again, the reason I'm putting the upper bound is x is because that potential energy is going to vary as it goes from x naught to 2x naught. And I'm trying to write a function for the potential energy. I'm not evaluating what the total potential energy is for that region. I'll show you what it looks like when I draw the graph to kind of explain the different ways of looking at this problem. But we're just going to evaluate it like this. So now I have negative b x naught times dx. So don't get confused with this x naught here. This x naught is not a variable. The x naught is a constant value. Okay, so this, when I integrate, this whole thing's a constant, right? So I just have some constant value, and I'm integrating with respect to x, right? So if I just have some constant value and I integrate it with dx, I'm just going to end up with c times x. Well, I guess I probably shouldn't have used c there because there's also this constant integration, but you get the idea. So here, when I evaluate this integral of negative bx naught, I get negative bx naught times x, and then I have to consider that minus sign in front of the integral. So I have negative, or actually, no, the negative signs cancel out, right? So I have negative bx naught times x, and then there's a minus sign in front of there. So I just have bx naught times x, and I'm going to, let's not forget our, well, we can, the plus c is just a constant value, so we can do it at the end. So from x naught to x, all right, and then plus c. All right, so when I evaluate this here, let's write it all out. So I have bx naught times x, right? That's my upper bound. And then my lower bound here is x naught. So I have b times x naught, which is bx naught squared. Okay, but we can't forget our initial condition. And our initial condition is that when x equals x naught, so at bx naught, all right, the potential energy at x naught, right? So potential energy at position x naught is equal to b, or I'm sorry, 1/2 bx naught squared. All right. So that's what I'm going to do for this function, right? So this function needs to be continuous. So I'm setting up these initial conditions at position x equals x naught. I know what the potential energy function has to equal, and that's where this plus c term kicks in. All right. So I'm going to set this equal to 1/2 bx naught squared. All right. And this is going to, so I have this function here. That's not my final answer because I'm not considering that I'm evaluating this integral from x naught to x, and I need to know what the initial condition is at x naught, right? So I need to know that the potential energy function has some energy, 1/2 bx naught squared, at position x equals x naught. All right, so that's where it comes in over here. So my c term, so it has to equal bx naught at x equals x naught. So then when x equals x naught, I have b x naught times x naught. That's bx naught squared. To have bx naught squared minus bx naught squared. Right, and then plus c. So then this is just 0. And then my c has to equal 1/2 bx naught squared. And it's basically the same thing they have over here, right? But it's just kind of explaining it in the context of the constant of integration, right? So you can think of this as your function here from the region x naught to x all the way up to 2x naught, and then you have this initial condition, the 1/2 bx naught squared, right? And then that's how they end up with the actual value. So I have this equation, bx naught times x minus bx naught plus c, and we know c has to equal 1/2 bx naught. So I'm going to write down bx naught times x minus bx naught squared, and my constant of integration is 1/2 bx naught squared. All right, and then so negative bx naught squared plus 1/2 bx naught squared, I end up with this function, bx naught times x minus 1/2 bx naught squared. And that's what my function is equal to here, bx naught times x minus 1/2 bx naught squared. And this is from the region of from x naught to 2x naught. Okay. And if I want to evaluate how much energy I have at 2x naught, okay, I can plug in a 2x naught here, and then I have 2 times bx naught squared minus 1/2 bx naught squared, and I have 3/2 bx naught squared. And then finally, for the last part, well, my force is 0, so the work done is going to be 0. I'll save the time of doing that integral. Yeah, integral of 0 is, well, 0. But I have this initial condition. So I have 3/2 bx naught. So 3/2 bx naught squared. And this is for when x is greater than position 2x naught. So this is the answer. All right. All the way out to here. So it's a bit much to also explain like why we're writing it out as a function, right? So why is it a function of x instead of the total potential energy? So that's, well, because that's what the problem's asking for. It's asking for a function, and it's not asking for the total energy stored from 0 to 2x naught or 0 to 3x naught. It's asking for a function. So now let's graph this function. So I'm going to graph the potential energy function, okay? So from x naught, no, actually, this is going to get messy. All right, I'm just going to do a quick little sketch. Actually, I liked using the thinner pen. Okay, so mu sub x versus x. Okay, so at position x naught, we see the function is basically a quadratic, 1/2 bx naught squared. So it's going to look like this. Let me use a different color. So it's going to be like a quadratic. Okay, and then at this position here, I'm going to draw a little dot there. It's going to go from being quadratic to linear all the way out to 2x naught. And then at the very end, in the region where x is greater than 2x naught, it's equal to some constant value. Right, so it's just going to be a constant value for the rest of the region. And if I want to plot these points here, right, so this point over here, this is the condition at x naught, it's 1/2 bx naught squared, 1/2 bx naught squared. And then up here, this value here is 3/2. All right, let me use this. This is getting cluttered. Okay, so this is 3/2 bx naught squared. Okay, so something else I want to mention here is if you evaluate the integral from 0 to x naught and then from x naught to 2x naught, what it's going to tell you is going to tell you how much energy is stored in the field over that region, right? So for the first part, it's going to tell you that the total energy stored by the conservative force, I said field, but right, so by the conservative force is 1/2 bx naught squared. And then from the region x equals x naught to 2x naught, and you evaluate the integral it's going to tell you that the energy stored from in that region is bx naught squared. But that kind of makes sense, because if I start at 1/2 bx naught squared and I end up at 3/2 bx naught squared, I mean, you can barely read that, so 3/2, but you can see it in the function, right? Then my change in energy, the amount of additional energy stored by the field, or by the force, is bx naught squared, right? And then finally, at the very end, it maintains a constant value of 3/2 bx naught squared. And that's basically what the potential energy function looks like. And that's all the different kind of interpretations of this problem, because otherwise it just looks like a bunch of integrals and we don't really know what's going on. It's certainly possible you still might be confused about this problem. If you want, we can go over it after school tomorrow if you're interested in asking questions. 'Cause I think this is a very good problem in terms of understanding the math, right? Actually using calculus to understand something that's happening within the physical system. It's a little goofy because the conservative force is changing, right? It starts off as a spring, and then it's a constant conservative force, kind of like gravity, and then the conservative force goes to zero. So it's, the only physical, I like thinking of things as like actual physical things in reality. It's like a regenerative brake system that's like jank, and then it breaks at 2x naught. That's the only thing I can think of that is remotely like this. But it's good in terms of like understanding the math that we're doing and why we're doing it. And specifically, these energy terms that they have in the solutions, right? So like the potential energy at 2x naught and the potential energy at x naught, that comes from like the constant of integration, right? And I prefer thinking of it in that way, because there's going to be problems, not necessarily for this class, but for, future engineering or, science classes that you have in college, where there's going to be more complicated initial conditions, and there's more stuff you're going to be doing with that constant of integration. But that's, physical use of the constant of integration. It's not just some, pure mathematical idea. So anyways, that took a lot longer than I anticipated. But going through the rest of this, all right, this is another problem that's a little tricky. So here we have to look at the power. And I'm going to keep it simple, because there's a lot that I can talk about for this problem, especially because they tell you to ignore from x equals 0 to x naught. Thank goodness, because that'd be very tricky. So anyways, here from x naught to 2x naught. Now it's asking about the power. So something to note about the power. We know that power is the change in energy over time, right? But the way we're going to look at this, we don't want to necessarily look at it in terms of change in energy over time, because notice it's a power with respect to x, okay? And we've done everything in terms of x. So the way we're going to look at it, right? You can also think of it in terms of work over time. So like how much work is done by the conservative force on the cart. And this is an equation I went over in class, where if we define work as the force times distance, right, we have force times distance over time is the same thing as like force times velocity, right? So the power, this is indicating, this is something else that's important. So this is the power delivered to the cart by the conservative force, all right? So if we look at this conservative force, we see this conservative force is negative, right? So there's potential energy being stored by the conservative force. It's taking that potential energy from the kinetic energy of the car. The car is slowing down in this problem, right? So like it goes down the ramp, it reaches some velocity at x equals 0, and then as the car goes along the bottom of the path, right, from x equals 0 all the way out to x equals 3 x naught, the car is slowing down. So the conservative force is taking energy away from the car, and it's storing it like this potential energy function. That's how the energy is being stored. It's going from kinetic energy to this piecewise potential energy function. So yeah, anyways, that's the basic idea. So something that's important to know about that is we're looking at the power delivered to the cart. So this is technically going to be negative, right? There's negative work done on the cart, right? The kinetic energy of the cart is decreasing. All right. And if we think about the power, let's think about this equation. So power is equal to force times velocity. Well, from x naught to 2x naught, let's look back at our equation. We see here that we're not even going to look at the potential energy equation. We're going to look at the force equation. So here, the force in that region that we care about, the force is constant. It's a constant force, right? So we have a constant force times the velocity of the cart. That's going to give us the power. Now, notice, as I was saying earlier, the velocity of the cart is decreasing, okay? And that force is a constant force. I have a non-zero velocity, so I start with some initial velocity or some velocity here at x naught, and that velocity is decreasing while there's a constant force being applied to it. All right, so I'm going to graph that. But notice that it actually doesn't go to zero, because at 2x naught, at position 2x naught, the cart's still moving, right? The reason we know that, it specifies it earlier in the problem. The cart continues to roll along the horizontal surface in the positive x direction. All right, so the cart keeps on going. It doesn't come to a stop. If the cart did come to a stop, then the power would eventually reach zero as the velocity approaches zero. But the velocity doesn't come to zero in this region. All right. Then from 2x naught to 3x naught, we see that the force is zero. Okay. So there's no force being done. There's no work being done on the cart because the conservative force is zero in that region. Once you get past 2x naught, going back to the analogy I gave earlier, that's when the regenerative braking breaks. All right. So the system breaks at 2x naught, and there's no more negative work being done on the cart. It's not going to lose any more kinetic energy at that point. So here the power is zero, right? So the power that is being delivered to the cart by the conservative force is zero for this region, and it is negative for this region. But importantly, it's negative and it is getting closer to zero, right? So the power that's being delivered to the cart is a larger negative value, right, at x naught than at 2x naught. And the reasoning behind it goes back to this, right? The velocity is decreasing as the cart goes across the, as it goes along the bottom of the track. Yeah, so the fact it has to be the correct sign, that's important, because we're looking at the power delivered to the cart by the conservative force, and we know that as the cart moves to the right, the force exerted on it is negative. All right, well, anyways, that's pretty much it for this one. And let's move on to number 3. All right, so yeah, in the interest of time, these ones are pretty straightforward. So here we have a lab, and we're going to be doing a lab tomorrow that's somewhat similar. So here what we need to do is we need to describe an experimental procedure to collect data that would allow the students to determine the energy of the launcher by making a linear graph. And here we have these different blocks of different masses, and we have a projectile launcher with some internal spring. So it's always compressed the same way. The only difference is the masses. All right. So in this experiment, I think the easiest way to approach it is basically we're going to use conservation of energy. We know there's energy stored in the spring, and it's going to deliver that energy into the block. All right. So the way we're going to be doing the lab tomorrow, and the easiest way to set up this lab, is basically what you're going to want to do is set up the projectile launcher vertically. Oh, actually, here, I got to be able to edit it. All right. So just set up your projectile launcher like this, and you're going to load the blocks in. The spring's going to be compressed, and it's going to launch the blocks upward, right? So the block's going to get launched upward. It's going to reach some height h, right? If you want to measure h from the floor, then we're just going to look at the change in height for the change in energy of the block, right? Because obviously at max height, the vertical velocity is 0, and we only have to worry about the potential energy, the gravitational potential energy gained by the block has to equal the potential energy that was stored in the spring because of the conservation of energy, right? Now, to write it out as an experimental procedure, hopefully we understand that if these blocks have different masses, they're going to reach different max heights, right? So remember, the potential energy is going to be mgh, right? Or in this case, I start off with some energy in the spring, 1/2 kx squared, and that's going to equal mg times delta y, right? Because the block starts off at some height above the ground, right? So we're going to consider that. We're looking at how much the block rises from its initial position, right? So a heavier block, because the energy in the spring is constant, right? This is the energy of the launcher, all right? We're not changing anything about the launcher, all right? So the blocks are all going to have the same final energy, but if the blocks are heavier, they're not going to go up as high, right? So a block that's twice as heavy, for example, is only going to go up half as high, all right? Or twice as massive, I should say. So to describe a procedure, basically with any good procedure, just make sure that you're clear and you, at whatever measurements that you're taking, that you take multiple measurements and you average them out. So here's a brief one that I wrote. So we're going to measure the mass of each block using a digital balance. And then we're going to orient the launcher vertically, measure the change in height of the blocks as they're launched, and then we're going to repeat the measurements for each block at least 3 times and take the average, right? So that idea of whatever measurement you're taking for the dependent variable, you want to take more than one measurement, right? You want to take, at least 3, honestly, as many as time permits, right? Don't go crazy with it. Don't do 10 measurements necessarily, but, doing, 3 measurements, 3 to 5 measurements, that's good to reduce any uncertainty, right? So yeah, that's basically it. So measure mass of each block, and it also specified the tools, right? I don't think I mentioned a meter stick. So using a digital balance, right, or using a mass scale, right, some tool that's going to actually measure the mass of the blocks. And then what are you going to use to measure the change in height, right? You're going to use meter sticks, or you can use meter sticks and video analysis to actually see what the maximum height is. That's the basic idea. So you have to specify the tools that you're going to be using, what measurements you're going to be taking, right? So measurements, we took mass and height, and we're going to use that to actually come up with a plot. So here we have to actually create a plot. So for the data collected in the procedure from Part A, describe how the students would create a linear graph and how that graph could be used to determine the value of the energy of the launcher. All right, so this one here it's not too tricky, but the fact that it has to be a linear graph, you have to kind of be careful with what you choose for your axes. All right, so I'm going to show you kind of how to think about this problem. So we know that the energy of the launcher, right, it's 1/2 kx squared, but that's just a constant that we can't change in the experiment. So that's one of the variables that we're holding constant. The things that are going to change in the experiment are going to be m and h, okay? Something else is important to note. Whenever you make a plot, you want to make the dependent variable your vertical axis, and then your independent variable your horizontal axis. All right, and the idea of this is kind of the idea of representing, data in terms of a function, right? So one variable depends on the other variable, right? As the experimentalist, the independent variables are the things that you physically change for the experiment, and the dependent variables are the things that change in response to your change, right? So we're going to change the blocks. The blocks have different masses. That's our independent variable. And the thing that's going to change that we're going to measure is the max height. That's the dependent variable. All right. Now, you can't just necessarily say, oh, for my dependent, it's h and my independent m, because that's not going to give you a linear plot. Okay. So we have to figure out, how do I represent this data to have it give me a linear plot? Well, one thing I'm going to do, I'm going to write it in the form of y equals mx plus b. We're not going to worry about the y-intercept for now, but we're just going to kind of look at, all right, so I need to get h as my dependent variable, okay? So I need to manipulate this equation, so I have h on one side of the equation. Let me put that in a different color. So I have h is equal to E L, that's the energy of the launcher, divided by mg. Well, my independent variable has to be related to the mass. G is just a constant, right? I'm not going to be changing that. So I'm going to write this out as H is equal to the energy of the launcher divided by G times 1 over M. All right, so I'm actually going to plot inverse mass. That way I get a nice clean graph where I can get a nice linear relationship, and I can use that slope to get some information about the system, right? And that's kind of like the whole idea of linearizing our data, right? So I'm going to have all the data of mass, all the data on the H, or I guess in this case, delta Y, right? Because it's going to start at some initial position, right? If we're going to measure it with respect to the ground. So here, I'm going to write delta Y. Actually, you can leave it as H. You can just say I'm measuring the height from the initial position, right? So you can just say that this is H. That's fine. So my height is equal to the energy of the launcher divided by gravity times inverse mass. All right. And then the idea with this is that this here, that's my vertical axis. My height is my dependent variable. My inverse mass goes on the horizontal axis. That's my independent variable. And then my slope is going to be equal to the energy of the launcher divided by gravity. All right. And that's how you want to set up your experiment. Right. So I specified it. Dependent variable is the height. Independent variable is mass of the block. And then to get the energy of the launcher, I'm going to take the slope, right? So the slope is something you're going to get from your graph, right? So you know that the slope is equal to the energy of the launcher divided by gravity. So if you want to find the energy of your launcher, just take the slope times the acceleration due to gravity, right? And that's it. Okay, so here they actually set up a different experiment where they know the energy of the launcher. They measured 0.452, and now they want to figure out the coefficient of friction between the blocks and the floor as they launch across the ground. So here they have some data, and what we notice is as the blocks get more massive, their final position is going to be smaller and smaller. And if you think about it, this kind of makes sense, right? So, I mean, if the blocks have the same mu, right? So it says the coefficient of friction between the blocks and the floor are going to be the same, right? So it's the same materials, same coefficient of friction. The only thing that's different is the mass. Well, if this block is on the floor, right, I know there's a normal force pushing up on it, and it has some weight, right, the force of gravity, which is equal to mg, and there's going to be friction that is going to do negative work on the block. So the block's going to have some initial kinetic energy, friction is going to do work on it, and the work done by friction is equal to, let's see, so I know that the friction force, it's similar to the one problem we did earlier. So it's just going to be mu times normal force, which is just mu mg, right? So the work done by friction is mu mg times d, right? So the distance that the object travels. And obviously, if they all have the same kinetic energy, right, because the spring is the same, right? They all are going to have 0.452 joules of energy. The heavier blocks are going to experience more friction, right? Because they're heavier, right? Mu mg times d. So the heavier blocks experience more friction. They're not going to go as far. And that kind of matches with our expectations. So what quantities could yield a straight line to use to calculate experimental for v sub k? So for this, we want to actually set up our equation, right? So our mass is going to be our, again, it's going to be our independent. That's the only thing we're changing. And the thing that we're measuring is the final position, right? So if I want to write this out, I know that the work done by friction is going to equal the change energy of the block, right? So I'm going to write that out. So the work done by friction is going to equal the change energy of the block, which is equal to this work done by friction. I wrote it out earlier, mu mg times d, right? And now what I need to do is this change of energy is the 0.452. I'll just write that as the energy of the launcher. Actually, I can write out 0.452. That's fine. We can just write out 0.452 joules. All right, that's how much energy friction takes away from the block. And we need to figure out how we can find mu sub k. So we're going to calculate mu sub k. So we need to set up mu sub k as the slope of our line, or the slope of our line has to have mu sub k within it. So again, I'm going to make my final position as part of my dependent variable, right? So I can rewrite this as mu times mg. My d is going to be xf minus x naught, right? So let's assume it starts at some initial position. Ideally, we just set it to 0. But again, this is just based on the data that we have here. And that's going to equal the energy of the launcher, the 0.452 joules, right? So here, what I need to do is I need to set up my independent variable, which is going to be the mass, but I need to set it up in the form of the equation for a line, okay? So I'm going to put xf here as my dependent variable. And if I rewrite this, yeah, actually for the sake of time, I'm going to do this. So I'm going to say x naught is 0. Ideally, to make lives easier, that's how it's measured. So let's just say that x naught is 0. And then for this, I'm just going to put energy of the launcher. All right, so I have mu mg xf is equal to the energy of the launcher. And then I'm going to divide both sides by mu mg, right? So my final position is equal to the energy of the launcher divided by mu mg. And m is my independent variable. All right, so again, just like in the previous experiment, we're going to graph inverse mass. Okay, and then matching that up with the equation of a line, here's what I'm going to graph. I'm going to graph the final position on the vertical. So on the vertical axis, I'll graph xf. On the horizontal axis, I'll graph 1 over m, inverse mass. And then the slope is going to tell me what the coefficient of friction is, right? So the slope is going to equal the energy of the launcher divided by mu times g, okay? So if I want to figure out mu, or mu sub k, I'll do the energy of the launcher, right, the 0.452 joules divided by the slope of the line times the acceleration due to gravity. All right, and that's how I would find mu sub k in the experiment. Now, the slightly annoying part is that you have to actually graph it. That's not too bad. You can just graph inverse mass, right? So just do 1 over m, write it in one of your data tables. We'll practice this tomorrow, right? Which is part of the reason I want to do like a lab FRQ hybrid, so we can just get used to this process. And you're going to have to plot the points on a physical graph. Something that's important to note when you plot the points, make sure you label your axes properly. So they give a sample response in here. So label your axes properly. Final position in meters, inverse mass in kilogram to the -1, because I'm graphing inverse mass, right? And then they're going to plot their data points. And when they give you data on the AP exam, they're not going to give you nice, neat, clear, clean data where a straight line goes right through all the data points. You have to draw a line of best fit that, you know, approximately goes through all the data points. So notice here I have roughly just as many data points above the line as I have below the line, and the distance from the data points in the line are, you know, as small as they can be, right? When you don't have to calculate linear regression, but you just have to kind of draw a line that, you know, fits through the data as best you can. And these little ovals here. So the thing is, when you look at the individual data points, that's actually not how you want to get the slope of the graph. What you want to do is you draw your line of best fit, and then you pick 2 points specifically on the line, right? So ideally you pick from end to end, but here they pick points near the endpoints that will give you sort of the best calculation for the slope. Again, we're doing this by hand. We're not using Excel or Google Sheets to plot the data or Desmos. Actually, I'm going to look into that because I know you do have access to Desmos. So we'll discuss that later. But yeah, if you physically plot the data by hand, you're going to want to pick 2 points on the line specifically in order to calculate your slope. All right, so let's see. Is there anything else to cover? All right, so you have your data, you plot it, you calculate the slope. With the slope, you calculate mu sub k, and I'm pretty sure that is it for this one. And we are almost done. So this is taking longer than I anticipated, but that's okay. So here, let's figure out this problem. All right, so we have astronaut on a small asteroid. So I can already tell you straight up with this problem, looking at it, the thing is, for this problem, you can't use the potential energy equaling mgh, right? So we're very used to using mgh for the potential energy. We're going to have to use the actual full equation. This mgh, that only works if the height that the object reaches is small compared to the radius of the planet. Here, we're not even on a planet. We're on a tiny little asteroid. So clearly, we're not going to be able to use the mgh relationship. The reason why you can't do that is because, well, the force of gravity isn't really constant, right? As you go really high up, the force of gravity is going to change, right? So we know the force of gravity is negative g m1 m2 over r squared. The potential energy due to gravity is negative g m1 m2 over r. And that's what we're going to use for this problem. So basically, the idea with this one is that you have some compressed spring. You're launching these 2 different spheres. And one sphere is heavier than the other sphere. However, they reach the same distance from the center of the planet. So I have sphere 1 and sphere 2. And what this is saying here is that sphere 2 reaches the same maximum distance from the asteroid, but he compresses the spring a different amount. So he compresses the spring a different amount such that sphere 2 reaches the same maximum distance. So it's indicating, how does delta x1 compare to delta x2? Well, if m2 is greater than m1 and m2 reaches the same max height, right? Well, I know that this, given that m2 is more massive, okay, there's going to be more potential energy between m2 and the asteroid versus m1. They're reaching the same height. They start at the surface of the asteroid, all right? And given that m2 is larger, okay, that means that energy had to come from somewhere. That came from the extra compression of the spring. So the spring, delta x2, has to be larger than delta x1 because the same spring launches a heavier, a more massive ball to the same height. Okay, so the only way for that to be true, if there's more energy stored in the spring, it's compressed it has more compression than in the original setup. And it says, without referring to manipulating equations, justify your answer. That's the basic idea, right? So let's see what I wrote here. So ball 2 has more mass and achieves a greater final gravitational potential energy than ball 1. And in order to achieve that greater energy, the spring had to be compressed a greater distance. And that's the delta x2, right? So that's the reasoning. Then it says here, derive an equation for d naught in terms of k, m1, ma, ra, delta x1, and physical constants is appropriate. Assume that the spring length and delta x1 are small compared to r sub a. All right, so for this one, we're going to use the potential energy function. Let's see, where do I have space to write it? I'll write it up here. Okay, so for part B, I know that my initial energy has to equal my final energy. For my initial energy, I have the compression in the spring, 1/2. Wait, actually, what is it asking for? So it's asking for in terms of M1 and X1. Okay. So 1/2 K delta X1 squared. That's the potential energy of the spring. But I have to include the gravitational potential energy. So the gravitational potential energy, like the full function, all right, it's defined as 0 when objects are infinitely far away, all right? And then as the objects get closer and closer, it's like a gravity well, right? So the potential energy due to gravity, all right, that function is actually negative. So we have to consider that negative when we're doing our conservation of energy. So I'm going to subtract the g times m1 times the mass of the asteroid. Actually, let me use the thinner marker. There we go. That way, because it's a little blotchy. Divided by the initial height. So the spheres start at r sub a, right? So the length of the spring, the delta x of the spring, is insignificant in terms of, they're both small compared to r sub a. So the initial position of the ball, we're going to say that it's at a distance of r sub a with respect to the center. So divided by r sub a. And then that's going to equal the final energy of the system. So when the sphere reaches up here, the velocity is 0, all the energy stored as gravitational potential energy. So that's negative g m1 ma, I think they use capital M, all divided by d naught. Okay, so that's my function. And now we have to solve for d naught. The algebra gets a little messy, but I'll set it up. So I have these GM1 MA terms here and over here. So I'm going to move this over here. I have 1/2 k delta x1 squared is equal to GM1 MA over r sub a minus GM1 MA over d naught. Okay, so notice I just took this term and I moved it over to the other side. Then I can factor out the GM1 MA. So I have 1/2 k delta x1 squared is equal to GM1 MA times 1 over r sub a minus 1 over d naught. Okay, and now I got to solve for d naught. So I'm going to divide both sides by this. All right, I'm just going to run through, because this has been going on for a while. So I'm just going to kind of run through the algebra steps. So I have 1/2 k delta x1 squared over GM1 MA. And then I'm going to move the 1 over d naught over here, move all this over here. So I got 1 over d naught is equal to 1 over r sub a minus, and I'll put the 2 in the denominator. Okay, and then I'm going to take the inverse of that. And that's kind of how they represent it. So here, this is going to be not the most pleasant looking function, but this is what the answer is. Okay, so I take the inverse to get an expression for d naught. So k delta x1 squared, all divided by 2g m1 ma. And that's my answer. All right, so what else we got to do? All right, so indicate whether the equation you derived in part B is consistent with the claim that you selected in part A. So let's look at our equation. So here we claimed in part A that delta x2 has to be greater than delta x1. And according to this equation, that's correct, because we know that both objects reach the same final height, d naught, from the center of the asteroid, right? So if I replace m1 with m2, right? So if I can rewrite this expression, it has to be equal. So 1 over r sub a minus k times delta x2 squared divided by 2 times g times m2 times ma, mass of the asteroid. Okay, well, let's think about what's going on here. If m2 is bigger, okay, these expressions have to equal each other. If m2 is larger, then delta x2 has to also be larger, all right, in order to obey the law of conservation of mechanical energy. All right, that's just how it is. They both reach the same max height, okay? So m2 is more massive than m1, so the spring has to do more work on the sphere, right? So it says here, indicate whether or not justify why the two answers are or are not consistent. And basically the reasoning here is consistent because they reach the same maximum distance, right? So given that m2, so we know that m2 is greater than m1, okay, then delta x2 has to be greater than delta x1. All right. More specifically, I think I put delta x2 squared has to be larger than delta x1 squared by the same proportion in order to reach the same maximum distance, right? So another way to write this is delta x1 squared over m1 has to equal delta x2 squared over m2. In other words, if m2 is twice as massive as m1, well, then delta x2 squared has to be twice as large as delta x1 squared because they both reach the same final height. So I think that's it. This is actually a fairly short one. So if you have any questions as you're working through these, just let me know. The test is not till Thursday, so there's still some time after school each and every day, especially for that second FRQ, right? Because so like in terms of like understanding what the question is asking for, like getting a potential energy function from a function for conservative force and vice versa, right? So one thing that these FRQs, we did this, we had some, we had to get mu sub x from f of x, right? So we did this, okay, but we never did the opposite, right? You can also do the opposite. So if you want to get the function for a conservative force, you can just look at negative du over dx. Okay, so you can also take the negative derivative. It's the negative integral of the force function times dx, but then the inverse is true, right? If I want to get the conservative force from a potential energy function, I take the negative derivative with respect to x, right? Or with respect to r, that's the general form, especially when it comes to stuff like gravity. But yeah, if you have any questions on those kind of problems where you're actually using calculus for the definition of potential energy, just let me know and we can go over some other examples from the multiple choice. And also, obviously, check out the multiple choice as well. I don't think there's too many, not like the last one, but any questions you may have, just let me know. You can also review the progress checks that you've been doing. It's been a fairly short chapter, so it's not really too much content. I feel like this is the only part that is going to trip people up because that's the only stuff that's really new, right? A lot of this other stuff we've seen before. It's just a matter of like actually being able to do problems that involve these the integrals and derivatives. But yeah, that's pretty much it. Again, just send me an email if you have any questions. Also stop by after school. But best of luck. Hopefully we do very well on Thursday.